Okay.
All right. So hope you enjoyed the coffee break. There's lots of delicious things out there. We're rounding out the first morning session with Matt Larson. So he's computer scientist, sysadmin for CMRC and MSET here. And so he's going to take you through some of the aspects of pre-processing. And I just wanted to highlight after this talk, we will have a photo session outside. So don't run away to lunch. Jackie will, well, not outside. Paul will help us find a suitable location unless we're putting on our winter coats. But so thanks, Matt. Take it away.
All right. I think today, for this part of it, it'll kind of step us back a little bit more towards some basics and get into just things about cameras, data collection, resolutions, binning, and things like that. But for the data preprocessing, here's the general outline of stuff I want to talk about. First, in general, just really briefly again about cryo-TM imaging and tilt series data collections. Talk some of the resources that we actually have at the MSET facility, and as those are the sources for our imaging. So I think it's good to highlight them. Move on from there to talk about the cameras that are on those instruments, and then different steps of the pre-processing workflows that we have basically implemented here to help do this on the fly. And so, as other people have mentioned before, this is really a great week to talk about cryo-electron tomography. And when I think about it, it's mainly we're taking tilted data collections of samples, and from those we're trying to reconstitute 3D volumes. And those techniques are really applicable to all sorts of different ranges of targets, everything from viral targets all the way up to eukaryotic cells, and to go inside of living systems and try to actually do things like subtomogram averaging to look at high resolution data that can come from multiple targets within a tomogram. Here at the MSET facility and also our co-facility, the SEMRC facility, there are multiple instruments that feed in as data sources. And one of them is the Titan Krios G4, which is part of the MSET facility, which has a Selectris energy filter and has a Falcon 4i camera on it, which is a very high frame rate, high resolution camera, basically the next generation for data collection. Likewise, at the SEMRC facility, the main instrument that we use for tilt series data collections is a different 300 kV instrument. It's the Titan Krios G3i, which has a bioquantum imaging filter and a K3 detector, which is the primary camera used for the tilt series data collection, but also has a Falcon 3 collector on it as well. And those are direct electron detectors, really well suited for tilt series data collections. Looking at the Gatan K3 camera first, it's a direct electron detector with 5K by 4K dimensions, capable of a very high frame rate, which is one of its real strengths. And so it allows for fast data collections, and it can store pixel intensities for each of the different fractions. Typically, when people are doing data collections, they're collecting a movie. So they're not just collecting static images, they're collecting a movie over time. And the subframes of that movie are called fractions, which enable different steps for pre-processing and improving the quality of the data. This camera can store in different formats, including the native DM4 format from Gatan. MRC is a really common imaging format that's used in different parts of almost every program for processing. Also, these support TIFF and LZW TIFF. LZW TIFF is what we primarily use in a lot of our data collections because it actually can let us reduce the size and storage restrictions of these different images that are collected. The Falcon 4 camera is another direct electron detector that's on the MSET Krios G4. This one is also capable of fairly high frame rates of 320 frames per second. And it has a new mode called the EER mode, which is an electron event representation, which is a native format. And in this case, you're basically storing not just pixel intensities on the different subframes, you are actually storing the events of the electrons hitting at different XY coordinates over time. And so instead of trying to track all the native intensities, which can be a large storage constraint, this actually can reduce the size further of images. And it allows for some other different properties and some challenges in pre-processing. These different direct electron detectors are also capable of super resolution imaging. And I just want to briefly mention this. So typically you'll have a direct electron detector will measure when an electron hits a different physical pixel on the camera, and it measures the charge that's hitting there, and then it reduces and identifies which pixel was hit. With super resolution imaging, you can actually go past the physical resolution of your camera. And both of the cameras that we have, the Gatan K3 or the Falcon 4, support super resolution imaging modes, where you're basically looking at the neighboring particles or neighboring pixels and saying that you can identify basically a subpixel, and this can be a twofold improvement of the resolution for that camera. We don't often do the data collections in the super resolution imaging mode, but it is another option for doing data collections. And then you can actually, in pre-processing or later workflows, you can reduce it down using something like Fourier cropping. Motion correction is one of the key first steps of pre-processing. Looking on the left side, you can see before there was motion correction algorithms applied to images, you basically had really blurry images. And one of the advances with the cryo-EM in general was the addition of doing collecting movies and motion correcting across frames. And so when you do this, you're basically tracking patches across the different subframes. Typically with a micrograph, you'll have something like 40 subframes. And then within those different subframes, there'll be patches of like 5 by 5 pixels. You'll be trying to track through different algorithms, which are oftentimes now GPU accelerated, how the different movements of the different pixels align between the different subframes. And then it does an averaging. And that averaging at the end improves the overall resolution by combining the pixels that are similar to each other, and reduce the blur that you'd otherwise see. And this kind of movement that can be happening here is often induced by the beam basically on the ice, causing a movement of the ice. But it also could be movements within the sample too. So when working with the K3 camera, we typically save our data as TIFF LZW and have a separate image gain file. And that lets us basically subtract later on from all the different frames, the gain file. And if there's like a problem in the data collection, such as an artifact, we can check whether it's something that was in the gain or it's coming out from an image. And sometimes you can recollect a gain and apply it later on. So there's different benefits of having a separate gain file. Another benefit is with the TIFF LZW, it also results in this smaller overall size for the images. With the Falcon 4i camera, we typically save as the native EER format, again with a separate gain file. And during the motion correction pre-processing, you can subtract that gain image file from it and do the gain correction. And that basically removes common artifacts that would be present across all the images. And then you also subsequently do the motion correction pre-processing. Different programs can do this pre-processing. There's UCSF Motion Core 2, Unblur. iMod has a component called Align Frames, and all of those are applicable for doing this motion correction. Motion Core 2 supports multiple GPU acceleration. So we use that, and that can help keep up with the incoming rates of data collections. And we try to do all this on the fly. Given at the bottom is basically an example for a Motion Core 2. You're typically giving it both the input format of the images coming in. The output is going to typically be MRC. You can define things like the patch size for the motion correction across the different subframes. You can give it the gain file. And then one of the things that is important if we have separate gain files is that you might have a rotation or flip of your gain relative to the images. And so that has to be applied. And so we do that during the motion correction. With EER pre-processing, the events are basically an X, Y, and a time for the different electrons. This can greatly reduce the data size. And one thing that's an additional benefit is that it can actually let users be a little bit more flexible in their subsequent processing. Here you can actually choose a different number of fractions and apply it during the motion correction. So you'll get still an overall number of subfractions. During the motion correction, you have to group those together. And so you group them as overall fractions, which become something that counts similar to like 40 fractions overall for a micrograph. And then you can apply the motion correction. There can be an input file called an FMIN file, which can define how you want to group these subframes together. And it can also provide information such as a dose that is happening for each of those frames. A raw ER would be many hundreds of frames, and that would actually be quite computationally slow with the motion correction program, so the grouping of it's necessary. We typically also do an upsampling and then do the Fourier binning back down again during the motion correction with our processing. CTF estimation I guess, is more generally applicable to single particle as an early step in pre-processing, but it can be useful as well to just give an estimate and say what's the quality. And so for this initial estimates, we might go to different programs like CTF Find 4 or GCTF. And IMOD has a built-in components for doing CTF estimation as part of your actual tomogram generation. There are different tilt schemes that can be used. And so as people are doing different data collections, there could be a unidirectional tilt scheme where it would just go from one extent to the other, or you could have bidirectional where it'd be going on both sides at the same time, and dosimetric schemes. And this can be important for your pre-processing setups because you will need to basically track the angles the different movies are collected at and build a stack which has them all organized in the correct order from lowest to highest. Stack generation can be with different programs. We're usually typically using IMOD-based tools such as NewStack or Align Frames. The goal here is that you have to build an overall MRC file, which would contain all the different motion-corrected images built together as a single stack. And given here is just an example with one of the programs that could pull in basically input files such as a listing of the tilt angles as a text file and a listing of the files of the different tilt images and recombine it together. One of the things that's nice after you've gotten a stack, and this is really helpful for trying to do automated pre-processing, is there's new tools that have come out. And one of the ones I'm highlighting here is a program called Aritomo. And this came out of UCSF. And it's basically a GPU accelerated, fairly advanced program for doing automated generation of tomograms. And so you can give it basically an aligned built stack of different images of your tilt series. And it'll go through these different steps, including course alignment, different rotational alignments, iteratively improving the alignment of the different tilts. And then it can do different back projection or SART reconstructions, which you can provide as options basically for this command line program. And it can do all this with GPU acceleration. So it can do it fairly quickly. We're seeing basically often between 5 and 15 minutes for the reconstruction of a tomogram with this tool. And kind of given here is another example just of a command. It's can be run as a command line program where you give it a stack as an MRC file. You can tell it the output. You have different parameters that you can apply with it, which can include the overall volume, which might be basically like a Z height that you expect for your tomogram to be built. Within that, you can say the overall volume for the alignment to be used. You can choose a binning. We typically are generating these tomograms in our pre-processing as basically like a first glimpse. And so we do have a binning of 6 right now, which basically just gives a smaller file size that you can quickly view. You can define different things like the pixel size, algorithms such as a weighted back projection to be used, a tilt axis angle if you know that from your collection, and things like enabling patch tracking. So we apply all these different options with it. And the resulting tomograms that come out of it can be used basically for a user to kind of go through and step. And we're trying to put these up online as our data collections are running, that you can look for issues that might be happening with your data collections and see generally if it's looking like the initial calibrations and setups are favorable. One of the things that we've implemented here as part of our facility is mechanisms for describing our data collections and collecting metadata that can be useful for feeding into like pre-processing or as a general note-taking. So we basically have a desktop application that you can get to easily through a menu at the instruments. Where you run it, it'll ask you different parameters about your user and group, or if you're an MSET user, it can specify your project. And those will help put the data into different buckets when it's going up online. We'll also have different attributes, such as people can describe their optics parameters, which is just, I think, useful for us generally to have that in our notes. All this stuff also gets tracked as a JSON data that we can put into things like a database later on, and look for basically like trends or issues over time. We also let people just describe things for, like, if it's a cryo-ET based collection, such as a collection with serial EM, where you're collecting multiple targets. We can define basically some information about how you want to do pre-processing at the start and about your tilt scheme. And this is just mostly useful for the notes for the tilt scheme, because still from each target, we can pull out other metadata from things like MDoc files if it's serial EM. But some of the parameters, such as the RE-TOMO ones, might feed into how you do pre-processing later. The net result for this is a lot of it's kind of happening in the back end, somewhat invisibly to users right now. It'll go on to, we have different facility servers, which will be running pre-processing. And some of the outputs will be motion-corrected micrographs that will be deposited in an evaluation directory. And so for every different tilt series, people with serial EM set up the tilt series in separate subfolders. So the different frames from each individual tilt series are kind of like separated from each other. Will, in their output, then also produce motion-corrected images in separate folders for users. It will also produce basically a stack that's assembled for these different tilts as a single file. And then the RE-TOMO output will include a MRC file, which is a tomogram that can be viewed, a bin6 tomogram, that you can have used to evaluate your tilt series collection at different targets. And all this is happening with a slight delay after your collection, but basically running it in parallel with your data collections, going up to our network storage. And then through different tools like Globus, people could be pulling this down as data collections are going, if they're remote users, or looking on our own local servers to see how collections are going. And we do have, one of our services is Globus. And so our data becomes available via Globus. And basically, as soon as it's on our network storage, it's available on Globus. Users from our local area have things tied to their network identities, which they can go and directly get to a bucket for their particular user. And if it's an MSET project, they can basically go to a project-specific folder that we share with them. And within those, we describe different data for different instruments, basically. On the back-end side, we have a bunch of servers in facility racks that do this pre-processing. Are kind of like a typical configuration for many of our servers is shown above, where we've got 4 NVIDIA GPUs. This generation was the RTX 6000s. Our current generation, I think we're on now A6000s, and looking at things like 4090s as kind of good GPUs to pick for targets to put into servers. These all typically also have large memory on the GPUs, which can be useful for other things for cryo-ET, such as if you're looking at large volumes of data, you basically want to have GPUs that have large memory capacity. And we do have some local storage on each of these servers, so we can basically mirror the data up there before it goes up to our network storage. In case we ever had an outage, we would be able to basically keep pulling in data and doing pre-processing on it. And these are more or less dedicated to on-the-fly processing. However, over time, we found that we really do need a lot of other different processing happening, and so we try to make use of these general servers for other facility items as well. Many of the software components that I've highlighted here are nicely available through a group called SPGrid. And SPGrid's out of Harvard, and they're basically a really nice way that you can register your lab or group with them. And they have these pre-built packages of different versions and very up-to-date for most software, supporting both Linux and Mac. And so I highly recommend this as a service. It's a great way to get well-maintained software. They're very responsive if you have issues or new packages that are coming out. And they have hundreds of titles for different cryo-EM and cryo-ET software packages. So many of the things we're using right now as part of a pipeline include things we pulled through there, including Aritomo, Motion Core 2, GCTF, and different things such as for Lion 4 as well, all available on SB Grid. And I think Elizabeth mentioned this earlier as well. We do have a website that you can go to if you have a project that you'd like to apply for time, either for training or services at these facilities. And this is available at www.cryoetportal.org. You basically, there's different project types on here, everything from training to service. And we do have a deadline coming up this end of this week. So if you have a cryo-ET project that you'd like to get started, you have a couple days still to basically assemble it all together. There's a requirement to have a PDF that describes your overall project and just information about the people who will be involved. And then you can go on this site and submit your project. And we hope you are encouraged to visit MCET as a facility. And I also hope that everyone here has a really great week. Just shown here are kind of a scattering of different instruments across the facility. We've got everything from plunge freezing instrumentation, such as EMGP2, VitraBots, VitraJet. We also have a Krios G4 instrumentation for the imaging. We have sample processing instrumentation, such as the FibSim, Oculus FibSim 2. Integrated fluorescence is built into that instrument. And we have different tools for doing analysis of samples, including mass spectrometers, and preparing samples such as with the Prebone technique. So it's a really great lab space, and I'm sure you all will enjoy seeing all these different areas this week. So I just wanted to give overall thanks to the different people who've been a really great part of this facility, and also the lab groups that really is kind of all together one big family here. The director, Elizabeth Wright, who is manning both of these facilities and building this whole operation. Alicia Boats, Kai, Alex Cotton, Anil Kumar, Priyank Mangola, Brian Siebert, Jack Van Twist, and Jay Yang constitute all the staff of our facility. We also have helping on the pre-processing side is DJ and Yan, who are undergraduate students here who are now helping with different Python building scripts. And we're currently trying to assemble a lot of our pre-processing workflows basically into a Dockerized and web-friendly format. So that's an ongoing effort. Also, I want to thank Mickey Woods, Tom Coombs, and Greg, who are all supporting Thermo Fisher members, keeping our instruments running, and members of the Wright Lab, including Dan, Joseph, Juan, Kaylee, and Vicky, who have all been great members in helping push the science forward. So I think I'll probably stop at this and just say thank you everyone for listening. Hope that was kind of a step back into pre-processing a little bit more on the basic side. So thank you.
Great, thanks, Matt. Anyone have any questions for Matt?
Thank you. My question is, if we are an external user coming to MCET for a tomography project, is the idea that we would use Globus to copy the data to our servers and do the processing ourselves, or can we keep using your servers for processing through your servers?
That's a great question. Ideally, definitely you will want to move all your data to your own local servers at some point and keep all your data as a copy. Typically with most facilities, there's a limit for how long just because of storage constraints. And I think ours, we have a policy about 3 months before it should turn over. But if you're a visiting on-site user, we do have computational resources on-site, including workstations that are all tied into the storage, and also facility servers that will be tied in with the storage as well. We're currently in the process of building out an HTC computing cluster, which will greatly extend our computing resources for people doing processing. I do have to give the note that part of the mission of the facilities is mostly on collecting the data, not doing the downstream processing, such as subtomogram averaging. However, as best as possible, we will definitely try to support. Thank you.
Oh, online questions? Okay.
Okay, the first question is from Shaq, and he says, is there an option of hardware binning in Falcon 4, just like K3 cameras? And the second question, would you suggest collecting tilt series data in CDS mode when using K3 camera?
The hardware binning question for the Falcon 4, I am not sure on. It's possible that someone else may know, and feel free if you do. But regarding the K3 question, we typically do collect all our data in CDS mode and would recommend that. That's pretty much the standard as we are using in our facility. It basically improves the quality of the data. So yeah, CDS mode is definitely the standard.
I was curious if anybody, or if you know people at your center who are using the RTOMO tilt alignments themselves alone to do sub-volume averaging, or if they're still going through iMod and doing it manually.
I think still within our group, we're mostly using it as a preview. So it's basically to generate initial tomograms. There are options such as you can put an option on it to create like an iMod folder that you could take that for downstream tasks in iMod. But typically I would say people kind of go in parallel and then do the manual pre-processing later in iMod and basically get an improved alignments and then use that or other aspects for downstream processing and subtomogram averaging.
Another question here. Do you use Serial EM or EPU Tomo 5 for data collection or another program?
The facility has both. We have both EPU Tomo 5 and Serial EM is set up on all our instruments. Our facility members favor Serial EM. I think there's a lot of benefits to it. Basically, it's a very flexible program. And it's one that you can actually do development in. And so some of the work that's come out of our group has basically been things that improve upon or add on to and work with Serial EM for data collection. I guess what I could highlight that there's a work that's being done for Montage cryo-ET data collections, which is very tied to Serial EM. But I think everyone also is available to use Tomo 5. And if you had training or a reason you'd prefer Tomo 5, I think that is a possible option here as well. And I would say that like EPU for a single particle, Tomo 5 is thought to be a very easy to use and polished interface, and that could be a real strength for it. So.
Okay, another question here from online. How does MSET recommends using the, sorry about that. How does MSET recommends utilizing the automated align stack? Should they be used for visualization only, or could they potentially be used directly for downstream STA? And if both, what parameters MSET recommends checking to evaluate visual inspections, statistics, etc.?
At this time, I would still say I think that programs like RTOMO are really great for giving like a preview, but not for downstream applications coming from it, based upon our experience. But it can be a great way if you are trying to go into this realm of high throughput data collections and you're really trying to collect many targets. One advantage of this is it basically lets you quickly preview and filter out and choose the best tomograms, and then really focus on that for your more advanced and better manual alignments later.
Okay, and one more. How much of a difference does a cold FEG make in tomography as compared with SFEG?
Can I turn that over to you, Liz?
So I can say we're still in the process of analyzing that in our workflows. So we've collected data, but we haven't finished the processing. There's Brian next to, nope, he doesn't want to answer. So that's where we're sitting right now. We've collected data on both and we're in the analysis phase. I'd say it's promising, but we're just not there yet. so everyone can- sorry.
What other application dates do you have if you can't swing the Friday deadline?
Well, right now it's set up as quarterly. So basically 3 months later, I don't know the exact date. I believe it's in July will be our next deadline. And so it's not quite rolling, but it's quarterly. All the applications are batched. They go out to a panel of reviewers and the top applications can proceed on. Otherwise, they'll typically be comments. And yeah, so.
We're happy to help you develop your applications as you're thinking about them. Matt and I talk to people a lot, and Brian as well, about what they're thinking about so that then you can polish it for a successful review. We haven't turned anyone away, I would say, for the national network. So
I guess the only limitation is that it can't include single particle type applications because there are a set of other facilities that are dedicated to single particle data collections as a national facility set.
Kind of as a follow-up to the applications, could you talk a bit about the differences between the 4 centers, if there are any?
Yeah, that's a great question. How it's basically set up with the CRI-OT network is that there are both spoke and kind of like hub facilities. MSET's designated as a hub facility. It also has a purpose as a spoke facility. The other facilities, CCT and CTU and SCSC are all classified as spoke facilities. All of the facilities have equipment for basic sample preparation, plunge freezers, ability to do milling to get thin prepared cells for imaging. MSET is set up with the Krios G4 for doing the data collection and imaging tasks. Anyone can apply, and when you apply for work at a facility, you can choose as a preference to go to any particular facility, spoke or hub, and projects can combine and carry over between facilities as well. There are probably differences in strengths between different facilities and particular techniques. But they all have a really good set of different instrumentation. And if you go on the website, you can actually see a layout. So for each of the facilities, different layouts of their equipment they have on site are available online. You can see the listings and go to also their own websites too to get more information as well.